Hey guys, welcome to the third digestive lecture. We are still dealing with the stomach, and we got to talk about what happens in there as far as absorption goes. And here's the deal: no nutrients get absorbed, none. Alcohol gets absorbed. Any type of alcohol gets absorbed. This is why drinking on the empty stomach can be bad news because the alcohol is quickly absorbed into the bloodstream through the wall of the stomach lining and then quickly exerts its effects. Aspirin, classic example of a drug absorbed in the stomach, which is good because then it gets to where the aches and pains are quicker. Other drugs can be absorbed in the stomach as well. So no nutrients, alcohol, and some drugs. Okay, what about the control of gastric juice production? Well, there's something called the cephalic phase. This is when you smell, you see, you taste food, so you know you're going to eat it. If you smell it, you're going to eat it. That's the way your brain works. And your hypothalamus is the guy in charge of this. He's going to tell the stomach via the vagus nerve. The vagus nerve is going to release acetylcholine onto the gastric gland cells. And the gastric gland cells are going to make more gastric juice in preparation for the eating of the delicious bacon and eggs. Okay, once the food actually gets into the stomach and the stomach stretches, maybe some protein digestion results in some peptides, it's going to kick in two reflexes, long and short. Long reflex, nerves from the stomach tell the brain, which I had a brain pictured right here. Imagine a brain right here. That'd be weird next to the esophagus. Nerves tell the brain, hey, I got food. Brain tells the stomach via the vagus nerve, all right, deal with it, make gastric juice. Meanwhile, the nervous system within the stomach wall itself will enact a short reflex where the stomach says to the stomach, I got food, and the stomach makes more gastric juice. Now, not surprisingly, this is the big phase. So the big phase of gastric juice secretion is due to the presence of food in the stomach. That should make sense. All right, what about inhibition? Okay, so our small intestine does not stretch so well. Remember, the small intestine has Plicae Circulares. It does not have circular folds. It does not have rugae. And so when the duodenum is a little bit uncomfortable because of chyme coming in from the stomach, when the duodenum is slightly distended, the duodenal endocrine cells are going to release a pair of hormones. One is called cholecystokinin, or CCK. The other is called secretin. And both these guys go tell the stomach, hey, stop. Duodenum is stretched enough already. Hold off on doing any more secretion of gastric juice, propulsion of chyme. Cool that for a second. So that is one big inhibitor of gastric activity. Another inhibitor of gastric activity is if the stomach becomes too acidic. So that'll actually decrease the production of gastric juice, which makes sense in a negative feedback sort of way. Last but not least, if you have increased sympathetic activity, whether that is from stress, anxiety, or fear, so sympathetic nerves are going to release norepinephrine upon the stomach, and it's going to inhibit the activity. Okay, a couple questions for you guys to do. Now, what has to happen to chyme once it gets into the small intestine? Well, remember, chyme is very acidic, so the pH is going to have to rise. We're going to have to neutralize the acidity of the chyme, and the nutrients are going to have two things happen to them. They're going to need to be digested and then subsequently absorbed. Okay, this is all going to get started in the duodenum, but the duodenum and really the whole small intestine can't do it on its own. The duodenum needs help from the gallbladder and liver as well as the pancreas. So let's review the pathways we met in lab. The gallbladder and the liver are both going to be involved in the delivery of bile into the main bile duct, or rather the common bile duct, right here. Meanwhile, pancreatic juice, rich in pancreatic enzymes and basic in nature, is going to travel down the main pancreatic duct. Those two guys unite at the hepatopancreatic ampulla, which empties into the duodenum. And then onward to the jejunum and the ileum, and these guys are all going to play a role in absorption and digestion. Okay, tell me how awesome the intestinal wall is. It is super awesome. It has a ton of surface area. All right, we're going to get surface area in three ways: with our circular folds, with our villi, and with our microvilli. Circular folds are big, permanent, remember they're folds that don't unfold, big permanent folds of the mucosa and submucosa. Not only do they increase surface area, but they slow down the passage of chyme. In other words, they act as speed bumps, giving us more time for the chyme to be digested and absorbed. All right, then the mucosa has finger-like extensions. So just to the mucosa, these are villi. They're chock full of blood capillaries and lacteals, which are essential for absorption, lined by simple columnar epithelial cells with a multitude of goblet cells in there as well for mucus production. Now, on the individual simple columnar epithelial cells, we do have microvilli, which are apical extensions of the plasma membrane, gives us even more surface area. The microvilli are often known as the brush border because of their resemblance to a paintbrush, to the bristles there under super electron microscopy. And there'll actually be digestive enzymes embedded in the wall here, like lactase, like the one we met in lab. Okay, now in between the villi, while the villi go up, intestinal glands or crypts of Leberkuhn are going to be there. They're going to secrete intestinal juice, which is going to be full of things like lysozyme, antibodies, mucus, enzymes, definitely. And at the bottom of the crypts of Leberkuhn, we're going to find some enteroendocrine cells. These are the cells that make the hormones like CCK, that we just mentioned a moment ago, and secretin. All right, well, that's pretty much it for the surface area adaptations that we have. And we need those, remember, to enhance surface area to facilitate both digestion and absorption. Now, the submucosa of the small intestine is kind of interesting in two places. It's interesting in the duodenum because there we're going to find alkaline mucus glands, and in the ileum because there we're going to find Peyer's patches. So on the left-hand side here, this is a slide of the duodenum. I mean, I can see these nice villi here. Now, this is my submucosa, muscularis externa, and in my submucosa, I do see a lot of mucus glands. These glands secrete an alkaline mucus, which is going to make sense because that helps us neutralize the acidic chyme coming from the stomach. Over here, this is the ileum. I have a collection of lymphoid nodules or follicles, and that collection is known as a Peyer's patch. The lymphoid follicles are made of packed immune cells, lymphocytes, macrophages, all the good things. It makes sense to have these in the ileum because of its proximity to the large intestine, which is so abundant. Sorry for that weird awkward pause there. Abundant in bacteria. All right, moving onward to the liver. The liver is involved in so many things. That's why one of our mantras this semester has been, when in doubt, guess the liver. Liver is involved in the metabolism of carbs, proteins, lipids, makes bile, makes plasma proteins like, what have we met so far this semester? Complement proteins, plasminogen, fibrinogen, prothrombin, other clotting factors, and we've met other ones too. Transferrin, albumin, all that good stuff. Plus, the liver is going to remove drugs and toxins from the bloodstream. Plus, it eats up old, ugly red blood cells, as well as stores vitamins, especially your fat-soluble vitamins, A, D, E, and K. Plus, stores minerals like iron, like zinc, like copper, like selenium, etc. All right, you did the anatomy of the liver, the gross anatomy at least, in the lab. We'll review a little bit of it here. I mean, the main digestive output of the liver, of course, is bile. Bile is going to be sent to the duodenum and or the gallbladder. Coming out of the liver itself are the right and left hepatic ducts. They unite to make the common hepatic duct, which we see here, which unites with the cystic duct from the gallbladder to make the common bile duct, which we know comes down and joins with the main pancreatic duct. And we don't see the hepatopancreatic ampulla here, but we know it's there. All right. Here we see the weird blood supply of the liver. Remember, all your digestive organs, plus your spleen, all your gut organs, their veins go and deliver blood to the liver before going back to the heart. This is weird but essential. All right, so the stomach, the intestines, stuff is absorbed there. It could be bad stuff, it could be drugs, toxins. Nutrients too need to be